Hey everyone, and welcome to The Explainer. I am so glad you're here today. We're jumping right into a really dynamic visual look at the foundational building blocks of plane geometry. We're going to break down the invisible scaffolding that basically makes up the shapes, spaces, and structures of the entire physical world around us. So, whether you're just refreshing your memory or looking to see these concepts from a totally new perspective, you are definitely in the right place. Let's get started. Okay, here's our game plan for today. First up, points. Then we'll connect those with lines and line segments. After that, we'll look at rays. Fourth, angles, where we measure the turn. And finally, classifying those angles by degrees. Let's jump right in. Before we even get to the definitions, I want you to chew on this for a second. What is the absolute shortest route between 2 points? And if you're spinning around in a circle, how exactly do we measure that turn? By asking these questions, we're not just doing abstract math on a chalkboard, right? We're actually using geometry as a highly practical, real-world tool for solving spatial puzzles. And everything we cover today is going to answer these exact questions. Section 1. Points. Geometry's building block. The zero-dimensional start.
So it all starts right here. All of geometry, no matter how wild or complex it gets, begins with a single point. Now, technically speaking, a point has 0 dimensions. No length, no breadth, no height. It's literally just a pure location in space. Kind of hard to wrap your head around, right? So we use everyday physical models to visualize this invisible concept. Think about the super sharp tip of a compass, or imagine a newly sharpened pencil, or the tip of a needle. The sharper that tip is, the closer we get to accurately representing that exact singular location in space.
Moving on to Section 2. Lines and line segments, connecting the dots. So what actually happens when we drop two distinct points, let's just call them capital A and capital B, and we try to connect them? Well, if you try a bunch of different winding routes, you'll see pretty quickly that the absolute shortest, straightest path is what we call a line segment. Think of it like this. Imagine folding a piece of paper and then unfolding it. That crisp, straight crease right down the middle gives you a perfect real-world picture of a line segment. It has a definite start, a definite finish, and those are its two fixed endpoints. But of course, geometry doesn't just stop there. Check out the difference between these two concepts. A bounded line segment is finite, meaning you can actually measure it with a ruler. But a true line? That's a whole different beast. Imagine taking that segment between A and B and just stretching it outward, past A, past B, literally forever. Because a true line extends endlessly in both directions, you can never actually draw the whole thing on a piece of paper. You can only draw a tiny snapshot of it. And remember, any 2 points will determine one and only one unique line that shoots straight through both of them. All right, Section 3, rays, endlessly in one direction. The one-way street of geometry. Now, a ray basically takes the two things we just talked about and mashes them together. It's a piece of a line that has a definite starting spot, an initial point, but then it just keeps going endlessly in one specific direction. A great way to picture this is to think of a lighthouse sweeping a beam of light out into the dark ocean, or even just clicking on a flashlight. The bulb, or even the sun itself, is that initial starting point, and the light travels infinitely outward from there. That, my friends, is a ray. Section 4. Angles measuring the turn, where rays meet. Okay. So what happens when two of those rays share the exact same starting point? Well, that shared point becomes what we call a vertex, and together the rays form an angle. Just look at this example of opening a notebook. When the book is completely closed, the covers are just resting flat on top of each other. But as you lift that top cover, you're rotating it. And the wider you open the book, the larger the angle gets. It's such a brilliant way to show that an angle isn't just some boring static shape drawn on a page. An angle is quite literally a measurement of rotation. The size of an angle is just the amount of turn you need around that vertex to swing the first ray over to exactly where the second ray is. Which brings us to Section 5, classifying angles by degrees, the language of rotation. Since we know an angle is all about turning, we need a standard system to measure those turns, right? Enter degrees. The golden rule here is that one full, complete rotation, like spinning all the way around until you're facing the exact same way you started, is exactly 360 degrees. Let's run through this quick cheat sheet. It makes it so much easier to categorize these spatial rotations, especially when you're busting out a protractor. Okay, so if the turn is tiny, more than 0 but less than 90 degrees, that's an acute angle. If it's a perfect quarter turn, exactly 90 degrees, boom, right angle. Keep opening it up between 90 and 180, and you've got an obtuse angle. Make it a perfect half turn, giving you a totally flat straight line. That's a straight angle sitting at exactly 180 degrees. And if you somehow keep turning it past that straight line, anywhere between 180 and 360, we call that a reflex angle. Let's actually apply this to something you probably look at a dozen times a day. It is so cool how this math perfectly decodes an old-school ticking clock. Think about it. A clock face is a full circle, right? So there's our 360 degrees. And there are 12 numbers spaced out around it, which means we have 12 equal gaps. If we take 360 and divide it by 12, we find out there are exactly 30 degrees between every single successive number on the dial. So let's say it's 2 o'clock. The minute hand is up on the 12, the hour hand is pointing at the 2. That covers exactly 2 gaps. 2 times 30 is 60 degrees. Fast forward to 3 o'clock, now it's covering 3 gaps. 3 times 30 gives us a perfect 90-degree right angle. Honestly, it's one of those amazing aha moments when you realize this invisible geometry is just hiding in plain sight. To wrap up our explainer today, I'm going to leave you with a little homework challenge. Look around the room you're sitting in right now and find a door. Is it possible to express the exact amount that door is opened using an angle? If you can, what physical part of the door represents the vertex, and what parts actually represent the rays? I highly encourage you to look around and spot the invisible geometry governing the physical spaces you live in. I promise you, you will never look at a swinging door or a ticking clock the exact same way ever again. Thanks so much for hanging out and exploring with me today, and keep looking for those angles.